All right, let's pull back the curtain and look at the secret sauce that makes our entire digital world tick. We're talking about the fundamental building blocks of all software, the recipes that power everything. We're talking about algorithms.
You ever been stuck in traffic and your map app just magically says, "Hey, I found a faster route"? Or how about when you finish a show and your streaming service immediately suggests your next binge watch, and it's perfect? That's not magic. Not at all. The answer to all of it is algorithms.
So, here's our game plan for the next few minutes. We're going to start with the big one. What even is an algorithm? Then, we'll see how developers actually sketch out their plans, and how they figure out if that plan is any good. We'll even learn the lingo they use to talk about it, and then wrap it all up with a little story. A tale of two loops.
Okay, first things first. What in the world is an algorithm? Honestly, the best way to think about it is just as a recipe. A recipe that tells a computer exactly what to do.
Now, the textbook definition sounds a little formal, right? A finite sequence of well-defined instructions, but all that really means is a step-by-step procedure. Seriously, that's it. If you've ever followed a recipe to bake cookies or used instructions to build some IKEA furniture, congratulations, you've used an algorithm.
Let's make this super concrete. Imagine I give you a totally random list of numbers, and your only job is to find the single biggest number in that list. How would you do it?
Well, you'd probably come up with a little plan, a recipe. First, you've got to start somewhere, right? So let's just assume the very first number is the largest one. Call it our temporary champion. Then, we just go to the next number and compare. Is this new number bigger than our champion? If it is, great, we have a new champion. If not, no big deal, we just move on. And we just do that again, and again, and again, all the way to the end of the list. And whatever number is our champion at the very end, well, that's our answer.
But here's the thing, not just any list of instructions gets to be called a good algorithm. It has to check a few boxes. It needs some kind of input, and it absolutely has to produce an output. Every single step has to be crystal clear, no ambiguity. And this is a big one, it has to stop. It can't run forever. And finally, each little step has to be something a computer can actually do.
So we've got our idea in plain English. But how does a developer take that and formalize it before they start writing actual real code? Well, that brings us to our next step, writing down the plan. And we're moving from a simple idea to something called pseudocode. Pseudocode is one of my favorite concepts. It's basically fake code. It's this awesome middle ground between plain English and a super strict programming language. It lets a programmer just sketch out the logic, the main steps of their recipe, without having to worry about all the picky details like semicolons and parentheses. It's the blueprint. And this is what it looks like. This is the plan for something called a linear search, which is just a fancy way of saying look at every item in a list one by one. Even if you've never coded, you can probably read this, right? It says, for each item, if the item is what we're looking for, print that we found it and stop. It's logic, pure and simple. Okay, so our algorithm works. We found the biggest number. Job done, right? Well, not so fast. Just because a recipe works doesn't mean it's a good recipe. This leads to a huge question in computer science. How do we actually measure performance? The official term for this is algorithm analysis. And really, it's just the process of figuring out how efficient our step-by-step procedure actually is.
And we mainly measure this in two different ways. The first is time complexity. Now, this isn't about pulling out a stopwatch. It's about counting the number of steps or operations the algorithm has to take, and crucially, how that number of steps grows as our input list gets bigger. The second is space complexity. That's all about how much computer memory it needs to get the job done.
Now, to talk about this stuff like a pro, computer scientists have a special kind of mathematical shorthand. So let's dip our toes into the language of efficiency by getting a handle on asymptotic notations.
I know, that sounds super intimidating, but the idea behind it is actually pretty simple. These are just tools to describe how our algorithm is going to behave when we throw a ton of data at it. We don't really care how it handles a list of 10 items. We care about how it handles 10 million.
Now, there are a few of these notations, but there's one that completely dominates the conversation. It's the one you're going to hear 99% of the time, and it's called Big O notation. You'll see it written as a big capital O.
So here's the absolute most important thing to understand about Big O. It always describes the worst-case scenario. Think of it like planning your commute. You don't plan for a Sunday morning with no traffic. No, you plan for rush hour on a Friday when everything is a total mess. Big O is about planning for the worst possible traffic.
Let's bring this home. Remember our linear search, where we're looking for one item in a list? What's the absolute worst thing that could happen? Well, the item we want is at the very, very end of the list, or it's not in the list at all. Either way, we have to check every single item. So if the list has n items, we have to do n checks, and that's why we call it O of n.
Okay, it's time to put all this together. Let's see how a tiny change in our recipe can have a massive impact on performance. It's time for a little story. A tale of two loops.
Take a look at this bit of pseudocode. It's pretty simple. We have a loop that counts up to some number n, but then inside that loop, we have a second loop that also counts up to n. What do you think that's going to do to our total number of operations?
Well, let's trace it. The outer loop is going to run n times. But for every single one of those times, the inner loop has to run its full course, which is also n times. So the total number of operations isn't n plus n, it's n times n.
And that gives us a time complexity of O of n squared, or big O of n squared. Now, if n is something small like 10, that's just 100 operations, no problem. But what if n is 1,000? Suddenly we're at 1,000,000 operations. And if n is 1,000,000, the runtime just completely explodes. This is how performance issues happen.
And that O of n we just discovered fits right here on this chart of common complexities. Think of this as a ranking, from best at the top to worst at the bottom. O of 1, or constant time, is the dream. It means performance never changes. O of n is what we saw with our linear search, and is pretty decent. But as you can see, once you get down to O of n squared and below, things can get slow fast.
So I want to leave you with this question. Now that you know a little about efficiency, and you've seen what something like O(n) squared can do, how does that change the way you think about those moments when an app on your phone starts to lag or a website just completely freezes? That little spinning wheel of death you see? You might just be looking at the very real result of a recipe that just wasn't quite good enough.